Hello students, myself Dr. G.B. Marali, Professor and Head Department of Mathematics, B. Bhumreddy College of Engineering and Technology, Hubli. So the topic given to me is Engineering Mathematics 2, that is second semester mathematics. The subject code is 15MAT21. In this subject I am going to cover, this is my first session. The syllabus given to me is Integral Calculus, that is Module 4. In this chapter I am going to cover double integrals, triple integrals, evaluation of double and triple integrals, evaluation of double integrals by changing the order of integrals and by changing into polar coordinates, and then the application of these double and triple integrals to find the area and volume. And also I am going to cover beta and gamma functions, their definitions and the relation between them, that is beta and gamma functions. Then I take the simple problems using beta and gamma functions. So these are the books you can refer. One is Higher Engineering Mathematics, that is B.S. Grewal, that you know already. Another one is the Advanced Engineering Mathematics, Erwin Krejcik. And also you can refer the good book, the Calculus, that is James Stewart, written by James Stewart. And another book, Advanced Engineering Mathematics, Gill and Cullen, is one more book. And you can also refer these two, the Pearson edition, Engineering Mathematics book, and one more, Engineering Mathematics by Davison. Well, this topic goals are, I am going to develop the methods for the evaluation of double integrals and the methods for developing the evaluation of double integrals by changing the order of integration. Methods are developed for evaluation of double integrals by changing to polar coordinates, and then the methods are developed for finding the area and volume using the double integrals, and also the methods are used to find the mass, centroid using the double integrals. Next, the methods are developed for the evaluation of triple integrals also. The methods are developed for evaluation of volume bounded by the surfaces using the triple integrals, and also to find the mass and centroid using the triple integrals. And then the methods are developed for the evaluation of triple integrals using beta functions, and also the methods are used to evaluate the integrals using gamma functions. You can visualize the concepts of double integrals here. The ability to visualize the plane figures and also interpret them as the areas, and to visualize the solid surfaces and you can interpret them as the volumes ones. The learning outcomes of this chapter, multiple integrals, are: upon the successful completion of the multiple integrals and beta gamma functions, it is expected that a student will be able to evaluate any double integrals for any plane regions, will be able to evaluate the double integrals by changing the order of integration, and also the students will be able to evaluate the double integrals in polar coordinates, and to evaluate the triple integrals for rectangular regions, and also to evaluate the triple integrals for regions bounded by surfaces or planes. Continuing that, students are able to apply the knowledge of these multiple integrals to find the area problems, to find the volume and mass, moment of inertia of the plane and solid regions, and also able to evaluate the integrals using the beta and gamma functions. So these are the tools some of the complicated integrals we cannot evaluate in general. Using beta and gamma functions, you can evaluate them. And also, you can establish what is the relation between beta and gamma functions, and then use it to evaluate some of the integrals. Now coming to the multiple integrals. So in this chapter, we extend our idea of definite integral. What we studied the definite integrals earlier, that idea is extended to the double and triple integrals of the function of 2 or 3 variables. Then these ideas are used to compute the volumes, masses and centroids of more general regions as well. We also use the double integrals to calculate the probabilities when 2 random variables are involved, that is which are available in probability chapter. Now we will see that the polar coordinates are very useful in computing double integrals over some of the typical regions. When the regions are circular or part of the circular, we use or we mean to convert the Cartesian system to polar coordinate systems, then evaluate using double integrals. Similarly, we will introduce 2 important coordinate systems in 3-dimensional space that are greatly simplifying the computational and of triple integrals over the certainly commonly occurring the solid regions, which are, one is cylindrical coordinates, other one is spherical coordinates. Whenever the region is a cylinder or part of the cylinder, we convert Cartesian to cylindrical coordinates, and similarly your region of integration is a spherical coordinate, spherical or part of the sphere, we convert the Cartesian to spherical coordinates, then evaluate. Now we start with the double integrals over the rectangular regions. We first consider the rectangular regions, then go for the general regions. So in this session we learn about double integrals and their evaluation of integrals using them to find the areas and volumes later. Now the double integrals over rectangles. Before going to that, just to go back to the definite integral process, just as our attempt to solve the area problem was by the definite integral. Now we seek to find the volume of a solid. In this process, we arrive at the definition of double integrals. How the area problem came from the definite integral. Now the volume, we arrive at the definition of the double integral now. Now coming to the review of the definite integral, how it was geometrically interpreted and how it was defined and what are the applications of definite integral. Let us recall the facts concerning about those definite integrals for those functions are of single variables. Now we see the definite integral. There is a function fx which is a function of one variable and is defined for the interval a less than or equal to x less than or equal to b. Now we start by dividing the interval ab into subintervals. We have the integration, that is the definite integral from a to b f of x dx. This is our definite integral. That is the intervals are given x equal to a to x equal to b, that is along the x axis. You take x equal to a is a line and x equal to b is a line. There is a curve y equal to fx, y equal to fx. So it is geometrically represented the area under the curve. Now we start dividing the interval AB into n subintervals, dividing the area into n number of subintervals. Intervals are given xi minus 1 xi. For example, I equal to 1, that is the first interval, x0 x1. So a is taken as x0, b is taken as xn. The next one is x1. The initial value x0, x1, x2, x3 and so on xn. In this way the interval is divided of equal width. Each of the interval, the width is same. Delta x is equal to b minus a upon n, means number of divisions are n in that interval. Next we choose the sample point xi star in these subintervals. In every interval we choose a sample points xi star, then take the summation of I is equal to 1 to n, adding them, f of xi star into delta x. Xi star is a sample point in each of the subintervals. Then you take the function values f of xi star multiply by the delta x. Then taking the limit of such sums as n tending to infinity. This is the limiting case. We are adding not only n number of this sum, infinite number of sum. That gives the meaning. See here, the definite integral of the function f from a to b is equal to, it is the limit of n tending to infinity, summation n is equal to 1 to n f of xi star delta x, put n tends to infinity. Now in the special case where f of x is greater than or equal to 0, that means the function is positive. All the function values are positive or equal to 0, then the Riemann sum can be interpreted as the sum of the areas of the approximating rectangles. You can see in the figure, these are the rectangles. This is the first rectangle, this is the second rectangle, third rectangle. It is nothing but the sum of summation of I equal to 1 to n f of xi star delta x. Those rectangles are infinite in number. That limiting value gives the definite integral of fx a to b dx. Then this represents geometrically the area under the curve y equal to fx from a to b. This you learned earlier. This part gives the area. That gives the area under the curve y is equal to fx from a is equal to b. That is the geometrical meaning of the definite integral from x equal to a to b fx dx. You can see in this picture there are some rectangles, finite number of rectangles here. The interval a, b is divided into n number of subintervals. First one is x0, x1, x1, x2, x2, x3, x3, x4 and so on. The arbitrary interval is xi minus 1, xi. This is a general interval and so on, xn minus 1, xn. It is the last subinterval. You can see there are the rectangles, portion of the rectangle is above the curve and in some cases the portion is below the curve. That means the sum giving the error, sum of the rectangular columns giving the error. Why it is giving error means if you increase the number of rectangles to infinity, this can be minimized. We have taken the finite number of finite sum, it is n I equal to 0 to n. This n tending to infinity, then take the summation of f of x star I. This is the height of the rectangle. Height of the rectangle f of xi star is multiplied by delta x, width. Delta x is the width of the rectangle. You know the area of the rectangle is height into the width, length into breadth. So considering the sum of such areas to infinite in number, sum of the infinite number of the areas, you get the value of the definite integral. Now after knowing the concept how the definite integral was evaluated using the Riemann sum, means dividing the interval along the x-axis into n number of subintervals, then that sum is taken to the infinite number, that gives the meaning of the definite integral. The same idea we can extend it to the double integrals. So in the similar manner, we consider a function f of two variables. In the earlier definite integral case, f is a function of x, only one variable. Now consider f is a function of two variables, fxy, which is defined on the closed rectangle. Here you consider the rectangle which is defined by a less than or equal to x less than or equal to b, and in y direction c less than or equal to y, c less than or equal to d. Consider the two-dimensional plane xy. Now x equal to a to x equal to b, x equal to a, this line, and x equal to b on x-axis, then y is equal to c and y is equal to d. So this is our rectangle which is bounded by a less than x less than b and c less than y less than d. So x and y are the intervals here. So R is the AB cross CD, the entire rectangular region, that is in R square. That means it is in the two-dimensional plane. XY is a point in the plane it is, that is why in R square. Now we have to assume that fxy is positive here. The function value, when you substitute x and y, the function giving the positive values greater than or equal to 0. That is our assumption. And what is the graph of f? We have to imagine in the definite integral the graph was a curve. Integration with respect to x, it is a single integral. Y is equal to fx, it is a curve in the xy plane. So what about f with the two variables x and y represents? So that is z is equal to fxy. This represents a surface in three-dimensional space. It is very difficult to plot. You have to imagine it is a surface in three-dimensional space, x-axis, y-axis, z-axis, that is origin. There is a surface, some surface, that is z is equal to fxy. It is in the three-dimensional space. You have to imagine for every point xy, there is a region, we can assume, there is a region, rectangular region in the xy plane, this region in the xy plane, and corresponding surface is generated. Z is equal to fxy represents a surface in three-dimensional space. Now you denote S. Where is S here? S be the solid that lies above the region R under the graph of f. You can see there in the picture, it is very clear. Z is equal to fxy, it is a surface in the space, blue color, it is a surface in the space, and R is in the brown color. R is a rectangular region which is bounded by x equal to a to x equal to b. This is the interval, and y equal to c to y equal to d along y axis. So combinedly you will get a rectangular region R. For those x and y values, this surface is generated. Putting x equal to y equal to values in Z, this gives the surface. Now where is S here? S is the solid which lies above the region R, above the region, rectangular region R, under the graph. This full gap, that is the solid under the graph f, that is defined as, this is a three-dimensional point that is in R3, x coordinate, y coordinate and z coordinates, that S is a solid in three-dimensional space, here it is, where z is defined from 0 to any xy coordinates. Those xy are belongs to the rectangular region. Now our main aim is to find the volume S. Where is the volume here? Volume under the solid surface under the z is equal to fxy and above the region R. Now the first step is to how we divided for the definite integral the number of divisions over the interval AB. In that way, first we divide the rectangular region into sub-rectangles. In the first integral, the definite integral, we divided the areas, number of sub-areas we divided. Now the region is the rectangular region. We divide the rectangle R into the sub-rectangles. How to divide them? First, we divide the interval AB. We divide the interval AB into m number of sub-intervals. Here, m number of sub-intervals. You draw a lines parallel to y-axis, m number of sub-intervals. Each interval of length, each interval is xi minus 1 xi. For example, I equal to 1, that is the interval x0 x1, that is the interval x0 x1, that is first interval. I is equal to 2, the next interval x1 x2 and so on. I is equal to n, that is the last interval xn minus 1 xn, and each interval of width is b minus a upon m, because we divided m number of subintervals. So the b minus a upon m gives the width of each interval, that is delta x. It is along the x-axis. Similarly, we divide the interval CD. CD is along y-axis into n subintervals. Similarly, we divide the interval CD into n subintervals. So that gives the small rectangular regions there. So by dividing CD into n subintervals, each are denoted as yj minus 1 yj. So j takes the value 1, 2, 3 and so on. For j is equal to 1, it is the first interval y0, y1. For example, this is y0, this is y1. That is the first interval. Similarly, I is equal to 2, that gives y1, y2, the next interval along y direction. Next is y3, y4, y4, y5 and so on. J is equal to n, that gives n minus 1, yn minus 1, yn, that is the last interval along y direction. And also each interval of length or width delta y is taken as d minus c upon n. How to find the width? The upper limit of y minus lower limit of y divided by n. N is the number of divisions. How many number of divisions we divide? That gives the width of each interval along y direction. How to get them? Next, we draw a lines parallel to the coordinate axis through the endpoints of these subintervals. You can see the picture, it is very clear. What I have plotted on the board, it is very clear from the graph here. There is an interval a to b along x direction. So we have denoted the subintervals. A is nothing but x0 here, x1, x2, x3 and so on, xi minus 1 and xi. This is general arbitrary interval, any interval xi minus 1, xi and so on. B is nothing but xn. So in this way we divided into m equal subintervals. Similarly, in y direction you can see C is y0, that is lower limit is y0, upper limit is yn. So y0, the next one is y1. This is the first interval y0, y1. Second interval is y1, y2 and so on. The last interval is yn minus 1, yn. So in this way the entire rectangular region bounded by A to B and C to D is divided into sub-rectangles. You can see many rectangles which are taken from the main rectangle. So number of divisions are made here. Now the width of each subinterval is delta x along x-axis. Delta x is b minus a upon m. Delta x is b minus a upon m. That is the width of any interval delta x. Similarly, delta y, that is d minus c upon n. D minus c upon n, width of each subintervals. Now consider the arbitrary rectangle. This is arbitrary rectangle. In the next picture you can show. We form sub-rectangles. We have done that. Rij, it is nothing but the arbitrary rectangle, any rectangle, arbitrary rectangle, that is obtained xi minus 1 to xi, xi minus 1 to xi, that is the length, yj minus 1 to yj, that is the breadth. So Rij is an arbitrary rectangle. Its area, you can say, area is length into breadth. It is a small rectangle, delta A. Its area, length is delta x and width is delta y. So delta A is the area of the rectangle Rij, area of rectangle Rij. Next, again in the same picture, we choose a sample point xij star, yij star in each Rij. I considered Rij is any sub-rectangle. Rij is any sub-rectangle. In that, we choose one sample point, that is xij star, yij star. That is one sample point. Similarly, you can how to select the other sample points. This is x star, x32 star and y32 star. How it is selected is in x direction 1, 2, 3, third block it is. In y direction 1, 2. That is why it is 3, 2. All the dots you can denote here. All the dots are the sample points in each of the rectangles. The one of the rectangle we chosen is x32 star and y32 star means 32 indicates 1, 2, 3. 3 rectangles. First rectangle, second, third rectangle in x direction, second rectangle in y direction. That is 3, 2 is given the notation here. So x star 3, 2, y star 3, 2 is a sample point in this rectangle. So in that way it is generalized. The Rij is a rectangle. The sample point is taken as xij star y star ij. That is a sample point here. Next, we can approximate the part of S. S I told you, it is the solid region lies above the rectangle, earlier I told, below the surface. Now I consider the small subrectangle from the previous picture, this one, small subrectangle Rij. This is Rij. So S is approximated by the part of S that lies above Rij, above this small rectangle, by the thin rectangular column, this one, corresponding function gives the column here. So that means the base is Rij, base is Rij, then the height of that rectangular box is f of xij star, yij star. So what we have done is the part of S, S is a full, it is, S is the entire solid region. We have taken the part of S that lies above the small rectangle Rij by a thin rectangular box. Corresponding to that, we will find a box here. Corresponding to that, the function values are defined. Fxy is defined for each fxy, xij star, yij star. That is the height of the box. So we got base into height here. In the next slide, we can compare the earlier figure and the latest figure. This is the given figure. The surface is drawn here, that is 3-dimensional surface, z is equal to fxy, and the given region is a rectangular region R bounded by A to B and C to D, that we have divided into so many sub-rectangles. In that, one sample rectangle, that is Rij, is considered. Rij, its length is delta x and breadth is delta y, and the column, that is the function, there is a sample point xij star and yij star. For that point you find f of xij star, yij star, that is the height, that is the column. So from the whole entire S into, we discretized into a small rectangular region and it's a column. Now the volume of this box, everyone knows that what is the volume of the box, that is height of the box times the area of the base rectangle. It is very simple. The volume is equal to the area of the base of the rectangle and its height, that gives the volume. We have taken one arbitrary small rectangle, that is the base of the box. Rij is the base of the box. Height is f of xij star, yij star, that is the height of the rectangular box. So the volume of that box is the product of the base into height. This is f of xij star, yij star into, this is the height, f is the height, delta A is the base. So height into base, that approximates the volume of the box. Now we have taken only one small rectangular region and its height. Similarly, go for the other rectangle. We have taken only one arbitrary small rectangular region, its base and its height we have taken. Similarly, go for all others. There are so many sub-rectangles. You consider their bases and their heights. So in this procedure, we follow this procedure, follow all the rectangles and add the volumes of the corresponding boxes. So we have taken only one box, its volume. So like that, we go on finding the other box volumes. Thus, we get an approximation to the total volume. The total volume of S is adding all the rectangular boxes. So that is why the double summation is taken, because it is in two direction. I taking from 1 to n and I taking from 1 to m and j taking from 1 to n. In x direction and y direction, you will find all the rectangular boxes. So their volumes are taken. F is the height of that particular rectangular box and delta A is the base. Delta A is same for all the rectangular regions, because delta A is delta x into delta y. So that total gives the volume. So we have come to the conclusion that volume is approximated, not exactly the volume is approximated by adding all the rectangular columns. Then you can see how the rectangular columns are taken here. This is the rectangular region in xy plane. Correspondingly, the sample points are taken. According to that, the columns are plotted here. So adding all the volumes of the rectangular columns, this gives the volume approximation. This double sum means, what is the double sum? For each sub-rectangle, we evaluate f at a chosen point and multiply by the area of the sub-rectangle. What we have done is, for each sub-rectangle, any rectangle Rij, we evaluated the function value at a chosen point, that is f of xij star, yij star, that is the function value, that we call it as height of the box, and multiply by the area of the subrectangle, that is delta A is the area of that particular rectangle, f of xij star, yij star, that is the height of the rectangular box. Then we add these results. So this our intuition tells that the approximation given in the previous equation, V is approximated by the double summation, that it becomes the better approximation as you go for m and n are larger. We have taken the finite number of subdivisions along the x direction and y direction. If you take m and n as infinite, if you take m and n are larger, means infinite, then add them, that gives the exact volume of the solid under the surface and above the rectangular region. This is the limiting case. Earlier we did, this gives the approximation, not the exact volume, because we added the finite number of rectangular boxes. We added the finite number, this is 1, so you may get here maybe 100 rectangular boxes here. That is not sufficient. Is the approximation, V is approximated by all the rectangular volumes of all the rectangular boxes. If you increase these boxes to infinite number, if you increase these boxes to infinite number, that looks like a total volume. Here it is not seeing the split twice the volumes are, you can see. If you increase m and n to infinity, the rectangular sizes becomes very small. So that looks like the entire volume. So the double integral is the limit of m and n tending to infinity and adding those infinite number of rectangular boxes, means volumes of rectangular boxes, that gives the volume of the solid. So in that expression, that to define the volume of a solid S that lies under the graph F and above the rectangle, what we told, this represents the volume of the solid under the surface Z is equal to Fxy, that is in the 3 dimensions, under the surface and above the rectangular given region, that is the rectangular region A to B and C to D. So is it the volume? Limits of this type appear in equation 4. They occur frequently, not just finding the volume, but variety of other situations. Even f is not the positive function. This is important. We considered here f is a positive function. Suppose f is not a positive, what happens? The sum of the surface above the xy plane you get, sum of the part of the surface below the xy plane. That time the below the xy plane, that is a negative value it gives, above the xy plane the positive value you get. If you add them, that is not the exact value. The above and below, if you consider both positive, that gives the entire volume which the surface above and below the xy plane. So that we need to take f to be positive, then only it is volume. F is not positive, just it is the value. It is the difference between the above volume above the xy plane and below the xy plane. So we make the following definition, come to the conclusion. The double integral of f over the rectangular region R, this we conclude that the integration, that is double integration of fxy dA, that is dx dy, that is the area, R is the region, is equal to the limit of m and n tending to infinity, summation I is equal to 1 to m, j is equal to 1 to n, the function values f of xij star, yij star into delta A. This gives the definite integral f is a function of 2 variables over the rectangle R. This limit exists, and if fxy is a positive, then you can say that the volume V of the solid that lies above the rectangle R and below the surface is this. We can interpret this double integral as the volume provided fxy is positive function. Otherwise you cannot say all the time it is a volume. If fxy is a positive function, then V is the solid above the rectangular region R and below the surface Z is equal to fxy. Now the double Riemann sum, this sum is known as the Riemann sum. The summation of I equal to 1 to n, 1 to m, j equal to 1 to n, f of xij star, yij star, this is called the double Riemann sum. Like the definite integral, only the single summation was there, that was Riemann sum for single integration. The double Riemann sum, if f happens to be a positive function, that is repeatedly I am telling, f happens to be a positive function, the double Riemann sum represents the sum of the volumes of the columns as shown here. I told already, the Riemann sum represents, that is double Riemann sum represents the sum of the volumes of these columns, is an approximation to the volume under the graph f and above the rectangle. I told you already, it is the approximation to the volume, that is the solid generated below the surface and above the rectangle R. Let me take one example to demonstrate using the double Riemann sum. Estimate the volume of a solid. The question is like that: estimate the volume of a solid that lies above the square. The region is a square region, that is 0 to 2 and 0 to 2, and below the elliptic paraboloid. You have to imagine what is the surface of this one. Z is equal to 16 minus x square minus 2y square. Its name is a paraboloid, elliptic paraboloid. The question is to find the volume of a solid that lies above the rectangular region. Rectangle is a square here, R is a square, 0 to 2, 0 to 2, above the square and below this surface. So we know that how to find the volume using the Riemann sum. So divide the region R into, first I take 4 equal squares here. R can be divided into any number of squares. First I consider R into 4 equal squares and choose the sample point to be the upper right corner of each square Rij and sketch the solid and approximating the rectangular boxes. You can see in the picture here 0 to 2 and 0 to 2. This is the given region, that is in the xy plane. 0 to 2, x varies from 0 to 2, y also 0 to 2. So it is a square region, that is R. The paraboloid is the graph of fxy. The given paraboloid is 16 minus x square minus 2y square. And one more thing, I divided the entire square region into 4 equal squares. Entire square region 0 to 2, 0 to 2 into 4 equal parts, equal squares. Area of each square is 1 because 0 to 2 is the entire square it is. If you divide it into 4 parts, 0 to 1, 0 to 1, so length into breadth is 1 into 1. So area of each square is 1 here. Now approximating the volume by the Riemann sum. Riemann sum tells that if m and n are 2, number of divisions are 2 here, that is the summation. The volume is approximated by I is equal to 1 to 2, j is equal to 1 to 2, the function f of xi, yi, delta a. See that f of 1, 1, delta a. In this figure, f of 1, 1 is the function value f of 1, 1. You can put x is equal to 1 and y is equal to 1, that gives f of 1, 1. And the area of that R11, f of 1, 1, delta a, f of 1, 2, f of 1, 2, this function value into delta a, f of 2, 1 into delta a, f of 2, 2. So there are 4 function values here into delta a. You can see here. You can calculate the values. F of 1, 1, that is 13. You can substitute here 16 minus 1 minus 2. So 16 minus 3, that is 13. Similarly, f of 1, 2, put x equal to 1, x equal to 2, that gives 7. Then x equal to 2, x equal to 1, that gives 10 here, f of 2, 1. Similarly, f of 2, 2, that gives 4. So delta a is same. Area of each square, subsquares are same, that is 1, 1, 1. So the volume is approximated as 34. Volume under the paraboloid above the region is 34. You can see in this picture. So this is our plotted surface, 16 minus x square minus 2y square. That is the surface equation. Below that you can see the 4 rectangles I have considered. 4 rectangular columns. I am adding the volume of all the 4 rectangles. That gives the volume approximation, that is the solid below the surface. We get a better approximation to the volume in this example if we increase the number of squares. So you can show I have done it through GeoGebra. You can see this demonstration. So in this graph we can see the rectangle given in this region 0 to 2, 0 to 2. I have divided into 4 parts here, 4 square regions. The same region in 2-dimensional is also there in 3-dimensional figure. This is the 3-dimensional figure. This red color indicates the surface, that is a paraboloid is given, elliptic paraboloid that is plotted. We are going to find the volume that is below the surface and above the rectangular, that is a square region 0 to 2, 0 to 2. So here we have done the number of divisions. Now the number of divisions, n is equal to 10. If you take, there are 100 square subregions. Accordingly you can see the smaller rectangular columns here. So I am adding all the 100 here. So n is taken 100 means, n is taken 10 means 10 by 10, 100 square regions. So I am adding 100 rectangular boxes, their values, that is a double summation. So in 3 dimensions you can see, if I increase n 16, I increase n is equal to 16 means 16 into 16 small squares you can see. 16 into 16 small square you can see. Correspondingly their rectangular columns in 3-dimensional. I am adding all the 16 into 16, 256 here rectangular columns are added. That approximates the volume. You can see the green color here, the total volume under the surface. You can move that surface, you can see very clearly that green color indicates the total volume under the surface, z is equal to fxy, and above the rectangular box. So here also you can visualize we have copied all the subregions. For 4 squares, this way the bigger rectangular columns are added here. If n is 4 means there are 16 columns, 16 rectangular boxes are added, that is better than the 4. Then n is 8, m and n are 8, 8 into 8, 64 rectangular boxes are there, n equal to 8. So adding all the 64 rectangular boxes, their volumes, that is a double summation, gives the volume of the solid. Here 256 means n is equal to 16 and m is equal to 16. The entire 2 by 2 square is subdivided into 256 square regions. Very small you can see, 256 square regions. Accordingly, you can see the columns and their base is the area. Small area you can see, correspondingly the height of the box. So height into base gives the volume of each rectangular box here. So the volume is approximated by adding all the rectangular columns which are under the surface. Surface is z is equal to fxy, that is the elliptic paraboloid, and above the rectangular region is given. See, the figure shows that when we use the 16, the volume gives 41.5. If we use 16, means 4 into 4, 4 divisions along x-axis, 4 divisions along y-axis, totally 16 square subregions. Those volumes are added, that gives the 41.5 is the volume. Similarly, if I divide more number of subsquares, m is equal to 8 and n is equal to 8, 8 into 8, 64 square subregions here. Okay, that volume gives the 44.875. If we add all those volumes of their columns, 44 point. And similarly, if I divide m and n are 8 into 8, 16 into 16, that gives 256 subcolumns, subsquares and their volumes, that is 46.46. You can see here, it will be shown exact volume is 48 here. That means we have started from 41.5 to 44.8, and m and n are 8, m and n are 16, 46.46. If you increase still m and n are more and more, the exact volume is 48 it is. Okay. Thank you for this section.